All right, so as I said, I'm Hunter Finney. Hopefully you know me by now. It should be. Maybe I need to get closer. Hello? Okay. Okay. So, for those who come to my lab sessions, you might know me as quite the psychologist in a CS world. Funnily enough, I'm the CS guy in a psychologist world wherever I go to my lab. And then when I go home, I'm a cognitive neuroscientist. And then everyone goes, ooh. But really, what I do on a day-to-day basis is very similar to what you are learning to do. And what that is manipulating and looking at data. But first, what is data? Well, data is a collection of information. Very helpful, I know. So, but really data is your Spotify Wrapped. It's your YouTube algorithm, your watch history, your stats on your best chess openings. It's everywhere and it's all consuming and it's all, in some realm, important and useful. And our job is to find what's important and useful. So I'm going to take us through a few studies today, and I'm going to hopefully get some feedback from you guys. We're going to do a historic example to start off with. This is a real problem that we faced after World War II. We had returning planes, and we plotted where the damage was on these returning planes. And the big question on everyone's mind is that you can only put so much armor on a plane. Where should we allocate this armor? So I'd like just some feedback, just like raising hands I'm just going to go through it real quick. On if you think it should be on the wings, raise your hand if you think there should be extra armor on the wings. Okay. Then there's the fuselage, so this is, where troopers might be carrying or payload. What do you think about there? Okay. And then there's this tail wing. What about this one? Do you think this is deserving more armor than the other wings for fuselage? And some would probably answer is that you take the average and just kind of put it all over, right? And just like a little bit everywhere might suffice. The one big realization that that these scientists had is that they only analyzed the planes that made it home. You can't analyze all the planes that were shot down. So their data was skewed. So all these were acceptable bullet holes. Well, these guys didn't make it home. And this is one example of data bias, particularly survivorship bias. So if you're filtering data and then not accounting for what data you're filtering, it might have a huge impact on what your results are. The survivorship bias, the name comes from this particular example. And I'm going to make sure I got that definition close enough. Yeah. Now, it's not all just doom and gloom. It's not all just rigorous studies. There's actually a lot of data coming into competitive gaming. So, one example of this is identifying overperforming items, or identifying if something's just kind of taking over the game or taking over the general meta that's happening. What's up?
Which game is this from?
This game is from Destiny 2. It is the PvP data of this week. I don't think there's a lot of active players right now, but I noticed this bias in this set of data. So you'll notice this is all the top weapons used this week in PvP. And at the very top, we have this weapon called the Martlet, which is used 15% of the time compared to the rest of the guns, the rest of the top performing guns being 4%. That's a huge jump. So you would assume this is an overperforming item. In a way to tackle that, typical developers would just lower the stats in that item, make it more in line with the rest of the playing field. However, it's not all just balancing. It's about optimizing fun at times. So this is, again, data from the last 2 weeks on League of Legends data. And here are the top performing characters. Notably, I want you to see like the win rate over here and the matches played. And those usually identify like the health of a character. Well, if we want to take a closer fine-tooth comb to matches played, we see that these two characters, Ezreal and Shyvana, are actually played hundreds of thousands of times, while the top performing characters are only played tens of thousands of times. And you'll notice that the most played characters are way down. And so you'll see like the majority of the player base is probably not having fun with their favorite characters. Imagine how many rows down just these two people take up. Now, instead of looking to balance outliers into making a more fair game overall, a lot of developers are going to optimize to having people enjoy their game. After all, video games are meant to be fun. I don't hear that a lot about League of Legends, but they're generally supposed to be for fun. Now, I want to talk to you a little bit about myself. So, there's also data and science, and I've been around a lot of awesome people in my work who all contribute to society, hopefully broadening our human perspective and knowledge. And they deal with all kinds of data. And I'm going to show you one data set right now. So, does anyone want to take a wild guess of what this data is, what it's trying to read, what it's supposed to be? What's up?
That's like a ID badge from
That is so unbelievably close. Surprisingly so. This is data from an EEG, an electroencephalograph. I can't say it. But it measures brain waves with magnetism. That's what it does. And so you'll see, this is what my girlfriend studies. She studies reading through EEG and eye tracking, and is really interested in the cognition part of reading and semantics. So we're interested in what are these schools telling us? So I'm going to talk to you real quick about what it means, and then we can see how powerful this data can be. So this is an example sentence. Our brains are prediction algorithms. We are always checking for the most likely outcome, and that most likely outcome is usually right. Interesting enough, this is how large language models also work. If we were to start a sentence, the cat sits on the, well, then you have a whole bunch of heuristics on where, what percent is the next word. And sometimes your guess is right. And so, for example, there's like 80% chance that we beat Matt based on our experience. Cool. Matt's next up in the sentence. That's most likely, and we see that, so we're right. And then we go with the 9%, and then 70% of the time we toy. Maybe they'll be with a ball, but that's not super expected, but it's still plausible. What my girlfriend studies is what happens when you read something that you don't expect. And you can measure that in your brain. So these lines here, these different colored lines, represent expected words, unexpected words, and unexpected words that just don't make any sense. So this is our example here. When the power went out of the house, or when the power went out, the house became blank. People would expect dark, lights go off. You might hear cold, like that makes sense. The AC goes, or the heat goes off. And then the anomalous one became half. Like that doesn't make sense. It kind of fits kind of how, how the words look, I suppose. That's a little too deep for right now, but like last time. And so you'll see the responses in the brain on accessing how much the brain is working. So this blue-purple line, you see it hugely spike. And that's accessing whether, like how hard you're thinking about searching for a vocabulary word. We're trying to match this vocabulary word to what's going on or the context is happening. So that's one example of science, and that might seem pretty far out of reach, but I promise you, it's really not. And so we're going to go over my own experiment, and we're going to work on this together to make a chart with the data that I've collected. So my data looks something like this. It's a whole bunch of rows, columns is a CSV file or an Excel file. What I am wanting to do is have people reach towards objects in virtual reality. And I want to know how accurate are those reaches, and I want them to reach across, over to the right as well. So straight ahead and then more to the periphery. And so we do that about 9,000 times across 50 subjects. And then we want to look at the data. And now, if anyone's gotten a head start on their assignment this week, this will be very familiar to you. So first, we import the data, where we make column rows, and then we open our file, and then we read the lines in. So now we have a whole chunk of lines as our data file, and then we would take each line, or this is the header. So the first row is just descriptors. So we just want to take those out. So, you might want to reference them later. So we do the first row, take those values, store it somewhere else. And then the rest of the rows, 1 through the end, we are interested in doing data on. So very, very familiar stuff for line and data lines. We're going to strip the white space and then split on commas. And then for every row, we want to assign this to a list. Further on, I said we use 2 VR headsets. One of these is going to be the Vario, and one of these is the Vive. And we have that marked in our CSV file. So if the HNB used column has Vario in it, well, then we know they used Vario. If it's a Vive, it's a Vive. So then we can split up the data again that way. So now we have all these trials with Vive and all these trials with Vario, and the headers are chopped off. For this experiment, I only did, I think that's 7 angles. There are increments of 5 out to 35. That's just hard-coded. And then we take the mean error. So this is very much like your exam where you took the average. We would take the target angle, where it's placed, and take their judged angle, and subtract the 2. Then we would add all those up, divide it by how many trials there are for that particular location, and then we return, and then we have a list of means for an angle, for a particular angle. And then we split those up based on the Vario and Vive. And then lastly, this is beyond the scope, but you can definitely probably read this. This is in Python matplotlib. It's to do plots. It's super powerful. There's tons of stuff online for it. I'd really recommend, if you want to do any graphing in Python, use this. And just like that, we have a graph, and then we can talk about it. So it goes from useless numbers, useless data that humans can't understand, to just 2 lines. And now we can make some inferences. So we can see as target increased, that each line goes up. Each line going up represents the angular error per target is increasing. Down here, there's 0. So in a perfect world, it'd all be 0. But we see as things go to the right, or yeah, as things go to your periphery, error goes up. We also see that the blue line, which is our vario, is much steeper than the red, our vive. So whatever is causing this error to increase, it's more so in the vive than is the vario. So that's a really interesting finding. We're seeing VR headsets show that people perceive space differently in two different headsets, even though they're supposed to be identical in performance-wise. And so you do a little bit of writing, a little bit of conjecture, talk about some other people's work, and ideally you get a whole publication out of that. And that's what my life is for the past 5 years. And you all have the skill to go on and do that. And that's really it for the whole presentation. I'll be happy to chat to you guys if you're curious about what I talked about today. What's up?
You want to do, like, what's the best way to go about doing data if, if you're trying to use, like, usable data, what becomes the point of what do you determine usable data and not usable data in that sense, specifically based on what the quantity outcome of the data is?
So that's the funny thing about science. Most of the time in science, you're trying to prove yourself not wrong, right? Like, and your experiment is supposed to be a non-biased way to do that. So, as an experimenter, we want everything to be equal. Everything okay?
No, you talk. I'm going to sit up.
Okay. Okay, so let me reframe this. What's good data and bad data? So there's really no such thing as bad data, is what I was trying to get. All data is good data, it's how you interpret it. So bad data would be if someone came in, I had to throw some subjects out because they were blind and went out, and they needed it in my study. It's like, well, you can't do a depth perception study, and I expect to understand the normal population if you're blind and went out. If they don't understand the task, if they're doing something completely different, that's another reason to exclude. But generally, you come up with what you're searching for before you run the experiment, before you collect the data. If you were to get all the data in the world, you can apply a lot of correlations. Like, I'm sure there's a lot of funny correlations online. I wish I had one on hand. It's like the price of bananas based on, like, the price of bananas in South America based on the number of traffic instances in the US. It's like, you can find correlations in almost anything, and that's part of the scientific process. It's just having a hypothesis and then testing it, rather than testing and trying to fit a hypothesis in. I hope that answered your question. I know it's like rambly. What's up? Yeah, so the question was, in my research, are we like doing mostly correlation? And that is not generally the case. So most of the statistics I run are detecting differences. So if something is different from another thing, there's a lot of different statistic styles. So that's, not quantitative. Frequentist. There's other Bayesian statistics that calculate similarity. And then correlation is a whole other part of that. So there's a lot of statistical methods people employ. For this data, the actual paper, I did a mixed linear model, mixed effects linear model, which is like big, like stats classy stuff. So no, it's not all correlation. If I were to do correlation, it'd be more on like a qualitative study rather than interview studies on like we did semantics, taking semantics as one using application, and then I would correlate that. So good or bad. What's up?
So you mentioned Matplotlib.
Yeah.
I know another popular one for data is Pandas. I'm just wondering, what do you think are the most powerful libraries for analyzing data, or what would you use in Pandas?
So I actually did this first pass this using Pandas for data analysis, but for presenting it, making a graph, Matplotlib, I really like, and that's mostly because I did that in data science, so I'm just used to it. Okay, so
Hunter will be here after, and if you have other questions, he also happens to be in labs on Tuesday, and he has help hours, if you would like to get more feedback. I'm sure he would love to talk to you about that, so please make use of that. All right, we are going to move on now